Hi, Ben with Novolux Stereophonic. In front of us here today I have a full set of Pioneer SX-1250 vertical boards. These are the circuits in the 1250 that are responsible for the power amplifier section. We have the regulated power supply or stabilizer board, the protection, and the left and right driver boards. In this video, I'm going to be going over diagnosing and repairing these circuits and testing and verifying them in kind of a unique way. A while back, I had a parts unit 1250. It was really trashed. It was missing a lot of cosmetic components, but the power amplifier was intact. So what I ended up doing was stripping down that chassis and getting it down to just the power amplifier section. And then I broke out the various voltages onto test points on some barrier strips and things. So I've kind of made a specialized way to test and verify these cards. And what that's going to allow me to do eventually is offer a service for rebuilding just these 4 cards. And that's what I'm going to be going over in this video. So if that sounds cool, stay tuned and we'll get started. Here's the test jig that I built for testing SX-1250 boards. It's simply an SX-1250 chassis that's missing the tuner in the preamp section. So the power supply and power amp are fully intact here. The heat sinks are just sandblasted and raw. This is because this thing gets moved around on the bench all the time. It's going to get scratched up. There's no reason to have it painted. It's just going to continue to get scratched. So I thought having these raw was just fine. I've got a IEC inlet here with a power switch, so I can easily switch this on and off, and I get an indicator so I know when it's on. Over here I've relocated a lot of the voltages from the power supply, so here I can adjust the plus minus 65, the lamp voltage, the tuner voltage, everything is available for me right here, so I don't need to tip it on its side to get to the measurement points or anything. So it just makes verifying cards really quick and easy. I originally built this because I work on 1250s all the time, and this thing has saved me in a couple situations where I've rebuilt a board and I put it into a fully built receiver and something's not working. It's not coming out of protection or something. And with this jig with a known set of reference cards, I can just put in a suspect card. If it doesn't work in here, then the issue's the card. So it's been very helpful for quick diagnosis when I get stuck on something. I've been wanting to offer a service for fully rebuilding these card sets for quite a while now. I've had a couple customers take me up on it. It's been successful, but I haven't captured the whole process on video, so I thought this would be a good opportunity. So I've got a full set of 4 cards from a customer. He's having issues with his SX-1250, and we think we've got it isolated to the power amp. So he sent me the 4 cards, and what we're going to do is verify that we can repeat the issue that he's having before we rebuild them, and then I'll take you through the whole process. I'm hoping that through this, you can see kind of what's involved in rebuilding these cards and if this might be a service that's right for you. I'll start off by saying that you do need a base level of electronics skill in order to pull off reinstalling the boards and getting everything aligned when they come back to you. So you need a little bit of electronics understanding and at least a digital multimeter, because we have to set the plus and minus regulated power supply voltages and the DC offset and the bias for each channel. So let's get started by taking a look at the diagnostic procedure that I did with the customer before he shipped the cards, and then we'll load up the cards and see if we can get this thing to fail. I've got the test jig spun around here specifically so that we can look at the pre-out main in section here. So in Pioneer they call it pre-out power in. This is where the audio signal leaves the preamp after it's gone through the tone circuit and the volume control and the filters and everything. And then this is where that signal enters the power amp. So in my customer's case, he was experiencing a noise or a crackling that was happening in the speakers after the unit warmed up. So our first order of business was figuring out, is this coming from the preamp or coming from the power amp? So the easiest way to do that is to pull the pre-out main in jumpers and power the unit on with no signal. So in this case, after he powered it on with the jumpers removed, the crackling was still there. So we know with a fair amount of certainty that the issue is in the power amp itself and not coming from the preamp. So sometimes the preamp can cause crackling if there's a noisy transistor or a really dirty intermittent control. So in this case, I had him, just to verify 100%, I had him feed a signal from the pre-out into a different power amplifier, and after listening for a while, there was no crackle. So his preamp is fine, but there's an issue in the power amp. So that's kind of how you would verify whether your issue is in the preamp or the power amp. If you find that the issue is in the preamp, sending me the card set is not going to do a whole lot. Perhaps rebuilding the power supply might help with the missing voltage in the tuner circuit, or if the regulated plus minus 65 are way out, the phono stage might be affected. So it's possible, but it's unlikely. So that's how you would isolate that. Let's move on to loading up these cards and seeing if we can duplicate this issue. I'm going to take this opportunity to kind of show how you would remove the cards from the 1250. I don't need to go over taking the bottom cover off. I'm sure you guys can figure that out. But one of the important things, if your 1250 was plugged in recently, you need to make sure that the main filter capacitors aren't holding a voltage. So you need to check and make sure these are drained. I'm showing 0 volts here, so I'm all good. Check the other ones up here. So what I'm doing is I'm checking across the ground bus and then the outside terminal on each of the caps. And there's no power supply voltage there, so we're safe to remove the cards. So the next step is I'm just going to pull all of these connectors here. And the reason I have to show this is because my reference set is loaded into this unit, so I need to take these cards out, but this kind of shows the process from start to finish, which is nice. Okay, next step, you need a fairly long screwdriver. There's going to be a Phillips screw on the front here and the back of each one of these boards. So the power supply and the protection board, after you remove the screws, those will just come straight out. But we need to remove a couple other things on the driver boards. Now we need to be very careful with this device here. This is a temperature sensing diode that's part of the bias circuit, and it's very easy to crack if you over tighten it. So that's more on the reinstallation, but here just be gentle when you remove this and make sure that you don't do any sharp bends or anything on this wire. These are kind of unreplaceable. There's not a whole lot of them left, and the process to make a replacement with modern parts is kind of ugly. So try to do a good job being protective of that sensing diode. Then we can remove the leads for the output transistors. And that's how the driver boards come out. Oh, I forgot this one. And you don't need to be super careful about marking exactly where they go back in. It's pretty obvious because of the way they hang. And they're also keyed. So you see there's a slot there. You can't plug this one in to that slot, for example, because this one's 3-pin and this one's 4 and there's a gap. You can get these backwards, this one and this one, so just make sure that the power transistors on this side get this plug and the ones on the back get this plug. Again, power supply can just come straight out. And I only have one screw in each of these in a stock unit. There's going to be a screw on the front and back of each of these caddies. So power supply just comes straight up. Again, we're going to be careful with this guy. Pull our 3 connectors. Undo the screws. It helps to have a magnetic screwdriver so that you can lift the screw out, especially on the back one. What I'm doing here is just holding the screw in with my screwdriver as I pull it out so I don't lose it. In the past, I've had people remove the cards from the brackets and just send the cards themselves, but I think in the future I'm going to request that customers leave them mounted in the bracket like this because it'll offer some rigidity for shipping. It adds a little bit of weight, but I think the extra protection is worth it. And then this can just be put down and taped on with a piece of painter's tape to keep it protected. The other thing with keeping the brackets installed is it allows me to quick swap between a reference card and a card under test without having to swap the bracket. So I think I'll definitely go with that on future ones, is keep the bracket attached if you're shipping these in. This is the power supply board that the customer shipped in. I just noticed some things that were kind of interesting on it that I wanted to share before I load it up in the bracket. So looking at the back, this appears to be a fairly low hours unit. There's not a lot of cold solder. Cold solder joints look kind of like this, where there's a little bit of a ring around instead of a nice dome. And that happens when the solder comes to almost a melting point and then cools down again. And when you start getting those, it can cause some intermittency. It's usually seen in high heat locations. Another thing that I noticed is these solder joints are shiny. And if we look here at this part, this is not an original part. This is an NTE device that somebody has put in at some point in the past. And some of these blue caps, I don't know if those are original, and the Zener diodes might have been replaced. So this might have been serviced briefly in like the 1980s maybe. So we'll be seeing the functional condition of this board in a bit. So I'll load these all into the brackets and then we'll put them back in the chassis. So here's the power supply board mounted back into that bracket. And I'm not going to show this in a bunch of detail because we're going to go through this whole process as an example of what happens when you get a full set of rebuilt cards back. So I'm going to go ahead and load this up off camera, and the next thing we'll do is do a initial dim bulb power on. So I'll be back in a sec. Remember that I mentioned that these things are a little bit fragile. On this one you can see one of the little wings on it has chipped off. This is what happens when you put it in and you tighten it down too much. So on these, when these get reinstalled, I just kind of slot them into place and just lightly come down with the screwdriver until it's snug, and just check that it's not going to wiggle out. Because we do need to thermally couple to the heatsink, but we don't want to risk cracking that case. I've got the card set loaded into the test jig, so next we're going to power this on under dim bulb. We're going to be observing the current draw of the amplifier at the bulb here. If everything's operating properly, this should flash bright as the power supply charges, and then it's going to slowly come down until just the filament is glowing at idle. So let's go ahead and power up and see what we get. That was the soft start relay and the protect relay. So this card set's in good shape. We do have just a little tiny bit of a glow there, so a little bit of idle current. So this thing is safe to work on. So the next thing I'm going to do is just see if I can feed a signal through it and see if we can observe that crackling that the customer was noticing. We're now looking at the output of the amplifier on an oscilloscope, and I'm just feeding in a low-level sine wave so that we can get a signal to look at. And what you can see is the yellow waveform is nice and steady, but the blue waveform is kind of distorting all over the place, especially at the top and the bottom of the waveform. So I'm going to connect a small test speaker, and we're going to listen and see if at idle with no signal, if we get a crackling sound out of the speaker, see if we can isolate this issue. I've got this little test driver hooked up to the right channel of the amplifier, which corresponds to the blue trace. Let's start the test signal. And you should be able to hear as that blue waveform distorts the, you can hear like a distorted sound in the speaker. Now, based on this symptom, this is probably going to be something to do with the protection relay. I had expected, based on the customer's report, that this would be something that would be audible at idle, but it seems like it needs a signal in order for it to present itself. So I'm going to turn on the test signal here and just manipulate the relay. So the speaker protect relay is right here. I'm just going to be using an insulated tool to put pressure on this relay as I feed a test signal in. So let's see what this looks like. So that's me putting pressure on the relay, and we can see that the signal is being affected by that. So I'm going to assume that that's the root cause of the issue. So what I can do is I can substitute in my known good protection card that has a fresh relay in it and redo this test, and we'll see if it resolves that issue. My reference protection card is now loaded into the chassis. I just turned it on. We should get a speaker protect click. There it is. All right, let's take a look at the scope and see if there's a difference. Okay, let's start the test signal. And look at that, nice clean waveforms. The blue trace is not bouncing all over the place. And just as another check, if we overlay these, the channel balance is near perfect. So this card set is actually pretty good besides the protect circuit, and it's most likely just a pitted contact on the relay. So later on we'll pull the relay and inspect it, and that's probably the root cause of this issue. Next up, I'm going to move on to checking the power supply voltages to make sure that the power supply is currently doing what it's supposed to be doing, and then maybe we'll ramp this up and see if this amp can produce full power in its current state. Okay, I'm now set up to look at the various power supply voltages. So the way that I have this set up on my test jig is I have a bunch of little pegs coming out here where I can easily connect the ground clips for my meters, and then I can come and measure at the various points here. So right now we're looking at the plus minus 24. This is one of the voltages that feeds the driver boards, and that looks nice and even and good. Let's go to the plus minus regulated 65. And these ones are adjustable. There's little trimmers on the board for this. So one of the things that I like to do is come in here and test and make sure that I can adjust these voltages up and down. In an ideal world, these are plus minus 65. Right now I'm at dim bulb, so I'm not concerned that we're a little bit low. And then the other power supply voltages that I have access to here are the power supply for the tuner, which is around 13.5, and then the lamps here, which are a little under 6 volts. So all of this is looking good for the power supply. Let's do a quick check of the bias for each channel. Okay, now I'm looking at the bias. I've got 45 millivolts of drop and 34 millivolts of drop corresponding to the left and right channel. The right channel is a little bit low compared to the left. I don't usually go crazy adjusting these pots because sometimes they can spike and cause damage. But you know, this bias circuitry is working, it's adjustable. I usually set these around 70 millivolts in the end. I've seen them as low as 23 and there's still no crossover distortion. I have a separate video on that about setting the bias, but we'll go over this in detail later. So this amplifier section seems to be healthy with the exception of that protect relay. So before I start tearing into this, I just want to do an output power test at full power off the dim bulb, and we'll see if this thing can get up to 160 watts. Okay, I'm now hooked up directly to an outlet. Start the test signal here. And I'm just going to start ramping this up. So right now we're at about 1/4 of a watt. And I'm just going to ramp this all the way up until we see clipping on the waveforms. There's clipping there. Back it off slightly. Creep it up again, right about there. And yeah, right around 160 watts. I'm going to start off by reworking the protection board. I'll pull the relay first and we'll take a look at the contacts and inspect that and see if the contacts show pitting that's consistent with what we're hearing and seeing on the scope. Then I will recap it. We'll do select transistor replacements. I usually replace this resistor if there's heat stress, which it looks like there is. I'll up the wattage on this and lift it off the board a little bit so that it doesn't continue to damage the board. A lot of the other stuff can stay, like the diodes here and the resistors are usually all fine. This is just rectifiers related to the main filter for one channel, and then I usually beef up that protection diode as well. So let's start by pulling the relay and then we'll rework the board. This is the connections for the relay on the back here. I'm going to remove this using a vacuum desoldering pump. In the past, I've seen if people remove these with a hand pump or with solder wick, sometimes it can end up lifting traces and it gets really messy in this area. So I'm going to try to do this cleanly and not cause any trace damage when we pull this original relay. Okay, let's take a look at these relay contacts. Right off the bat, you can see that this piece here is discolored and there's a little bit of corrosion or oxidation here. Oh yeah, that's not looking too good. So on these, what I do to clean the contacts, and in this case, I'm not going to keep this relay. We're going to put a brand new relay in, so I'm just showing this for demonstration purposes, but I can remove this little spring and then we can just pull the contacts out and get a closer look. All right, so let's look inside. We can see there's definitely, like, the contact surface is completely compromised on this side of the relay, and that is one that's making contact. Then on this side, you can see heavy tarnish on the 3, and this one, this must have experienced some sort of high current failure. It's kind of blown apart there. So that's what we're dealing with there. So I'm very certain that this is the root cause of the issues that the customer was originally having. So just replacing this relay is going to go a long way, but we're going to do a bunch of additional work just to make this protection board stable for the long term. Here's the rebuilt protection board. I just want to go over what I did again. Of course, the relay itself was replaced. We saw that that original part was in really rough shape. Luckily, there's a good drop-in replacement available. I also replaced all of the electrolytic capacitors in this circuit. This resistor and this transistor are part of the 35 volt regulator circuit. This unit this board receives about 65 volts from the main power supply, and then it drops it down to 35 volts to power this circuit. So this resistor tends to get pretty hot. I end up extending the leads a little bit and adding a higher wattage part just to keep the heat in the legs down so that it doesn't transfer the heat down into the PCB and damage the PCB and the traces. This transistor is doing some heavy lifting in that voltage regulation circuit, so I put a larger, higher dissipation part there. Likewise, this one I also up a little bit. This transistor directly drives the relay coil, so if this ends up getting weak, it won't be able to close the relay, or it might not close all the way. This diode I up to a beefier part, again for flyback protection. This transistor here is stock, the same as these two, 2SC945, but they don't tend to fail in this area, in this circuit. But here, the responsibility of this transistor is to drain off the time delay capacitor after the unit is powered off. So it's letting some current flow through to ground, and I guess it's just a situation that's a little bit too hard for that transistor to handle for a long term. So we do see a lot of failures of the 2SC945 in this circuit, so that I beef up to a higher dissipation part so that it will have a little bit more longevity. In this circuit here, I don't tend to replace these transistors. These are responsible for sensing the various error conditions for the 1250. So the 1250 has three protection modes. First is power on delay. It also does DC offset protection, overcurrent protection. So when you power on the 1250, this capacitor here charges, provides a time delay. It's about 3 seconds. So after you power on the unit, there's a short delay and then the relay clicks. After you power the unit off, this transistor drains down the capacitor and the relay will open again. If either of the channels has high DC offset, this circuit will keep the relay from closing. If we have a overcurrent condition, that's also sensed here. So if either channel starts drawing heavy current, if there's maybe a shorted speaker, or you're driving a low impedance load at high power and it drops below a certain threshold, this circuit will detect that and also open up the relay to protect the system. So that's everything that's going on here. I'll be testing this circuit in detail, so we'll be forcing the 1250 into all of the various protection modes to make sure that all the circuits here are functioning properly. Next up is the protection board, and I treat this one completely different than the protect and the driver circuitry. So in the other boards, I do a more conservative parts replacement, only the stuff that I've seen fail in the past, and preventative maintenance on certain transistors that are prone to failure based on information I have from other units that I work on. So on the power supply, conversely, I gut this thing and basically rebuild it from scratch. It's going to get all new capacitors, all new silicon, both diodes and transistors, new trimmer resistors. There's going to be new transistors for the plus minus 65 pass elements. This thing is, I basically got it down to the resistors and these diodes and rebuild it. The reason being is this is a high stress area. All these parts are doing heavy lifting and they're exposed to a lot of heat. These small ones near the heat sinks here almost always fail. These larger ones tend to hold up okay, but a lot of times you see shrinkage. There's just a little bit here where you can see the wrapper is starting to shrink out towards the edge. But overall, this power supply must have low hours, because usually there'll be at least one in here where the entire top of the wrapper is shrunken down and you see a completely silver top. So either some parts have been replaced in here in the past, as we saw with this transistor, or this is a very low hours unit. In any case, next up, gutting this thing, and I'll come back once I have it gutted. We'll test the resistors and then I'll rebuild the whole board. This is what the power supply board looks like after I've gutted it. All of the parts that are removed, I'm going to be putting brand new parts in their place. I have a little bit of cleanup work to do before I get started. Underneath where all these caps were, some of this, I don't know if it's physical leakage or what, but there's usually always some sort of residue below the electrolytics, and then I'll get this glue removed here. The other thing that I do while I've got the board in this state is I measure all of the carbon film resistors that are left on the board to check them for accuracy. With all of the components removed, that allows me to get a very accurate measurement without external capacitors and stuff affecting the reading. So do that there. And then out of all the stuff I pulled off of that board, there was only one bad capacitor. That was one of these little guys. So high ESR, it's supposed to be 22 microfarad, 10 volt. So it's just gone high ESR on us. So usually I see a lot more of these. Almost all of the smaller capacitors are bad on the well-used, well-loved boards. This method that I'm going to be using with gutting the board like this, I do not recommend doing this if you are following along and doing your own boards. The reason being, it's very easy to make a mistake and put something in backwards, and at that point you've lost a reference. Pictures are great, but there's nothing better than looking at a physical piece, how the capacitor went in beforehand. So when I do this gut rebuild like this, I have a completed reference board that I use to get all my capacitor polarities correct, all the transistor pinouts correct, and stuff like that. So you can do it this way, but you're a lot more prone to make a mistake if you gut it like this and you don't have a physical reference. Here is the fully rebuilt power supply board. One of the things I'd like to do here is angle this 22 microfarad cap up and away from this device here. This is the only cap that had failed out of the original parts, so I like to do that just to get it away from that heat source. The last thing that I need to do on this is take care of some stuff on the back here. So when I had it torn down to just resistors, I went ahead and reflowed all of the joints. If you remember in the beginning of the video, I mentioned cold solder joints. So by reflowing them, you just mitigate any of that from causing an issue in the future. And then you see these kind of ugly, dirty looking lines on the back here. This is all old flux from the original process of creating the board. And this can end up looking a lot nicer if I take a little time with it. So I'm going to go ahead and clean this board thoroughly so that it looks really nice for the customer. Even though it's getting mounted eventually inside of a that black metal mounting bracket, I want the customer to have a good experience when they get these boards back. So I'm going to do that next, and I'll do that to the Protect board as well while I've got the materials out. Here are the protection and power supply boards with the flux removed, so you can see the difference there. I also like doing this because it allows me one final opportunity to inspect all of my solder work and make sure that I didn't improperly flow anything or miss any of the cold solder joints. So that's all done. These are ready to go back into the chassis for testing. I do need to polish and clean all of these connectors on the bottom here. I'm not going to show it on these, but I will show that in detail when we do the driver cards. Got the rebuilt protection and power supply boards loaded into the chassis. The driver boards are removed. I like to do it this way just so that I'm not testing multiple variables. Right now I just want to make sure that it passes the dim bulb test, the relay clicks, and that I can adjust my plus minus 65 volt rails and all the other power supply voltages are present. So let's go ahead and turn it on, and we'll watch the dim bulb on the left. That looks good. First click was soft start. There's my protect relay. Here are my regulated plus minus voltages. I just want to check and see that these are adjustable. So this is the plus that I'm on right now, and that looks fine. I'm just going to put it around 63. It's kind of where we were before on dim bulb with the original board. And just need to make sure I can go up and down. Okay, bring that one back to 63. And let's check our other voltages. So the plus minus 24, I'm using Zener diodes. They're pretty well matched, but they're 24 volt Zeners, but they always test around 23. So this usually ends up around plus minus 23. And those are very close. The main thing is I try to match the Zeners so that I have very close power supply tracking. So with the original diodes, it was plus minus 24. Now it's plus minus 23. It's not a huge deal there. That is all looking good. And then let's look at the 13.5 and the 6 something. Yeah, so all the power supply voltages are good. The relay clicked. That's all I need to know from this test. So these boards look fine. I'm going to go ahead and move on to the driver boards. Okay, just two boards left to do, the left and the right driver. These are pretty straightforward to work on. I just do the 4 electrolytic capacitors. There's a tantalum here and this associated transistor for the overcurrent detect, which I replace. And then I usually do the differential input pair so that this is better DC offset stability, but the rest of the transistors in here hold up really well. For these, I usually pull this heatsink and refresh the thermal compound in the micas here, and then bias and DC offset trimmers. So these will go pretty quick. I'll get these done and we'll take a look at them once they're finished and then polish out these connectors. Here are the reworked driver boards as outlined. Came out really nice. I also did the flux removal, same as the other two boards. Now, if you're following along with this video more to learn how to do this type of audio service yourself and you're interested in that technique, I actually learned this from a friend of mine, Connor. His channel is Prime HiFi. So if you're interested in that technique, definitely check out his channel. He does a lot of restorations on extremely high-end vintage electronics and just does a really thorough job and a good job explaining the techniques as well. So definitely check that out. The last thing that I need to cover on these boards is cleaning the pin connectors. So this top row is all silver plated, and these pins develop a dark tarnish. Now if we look at the bottom there, you can kind of see it at the base of the pins there. I'll give you a better example. This is a board from a 1250 that I haven't started on yet, and this is a more typical way that this tarnish looks after years. So even though these have already been done at some point in the past, I'm going to touch them up and I'll show you that technique now. Okay, in front of us here I have a good example of this silver tarnish. This is from a different protection circuit, but I use a product called Brasso. This is just a very affordable metal polish, so I'm just going to be using Brasso on a cotton swab. Zoom in here. I'm just going to go on this first pin here. And the polish is just a mild abrasive, so I'm just cutting through this first layer of tarnish that's built up on top of the connector. So you can see the before and after here, looking at these dirty pins in this one here. Then I'll hit it with a little bit of isopropyl alcohol just to clean any of the remaining polish off. And then the final step will be just a little drop of deoxit D100. You can use D5, you can just spray it onto a cotton swab. I have all the different deoxits handy. I prefer the needle applicator for stuff like this, but then I'll just put a thin layer of deoxit on the pin itself. And I like to do this right before I load these into the chassis, because that way I can kind of work that deoxit into the female end of the connector. So that's the pin cleaning process. I'm going to go ahead and complete this on the 2 driver boards, and then we'll load everything back into the chassis and do some more testing. The full card set is now back in the chassis. I'm going to do my initial dim bulb power on. Soft start and protect. It's good that the protection came in. That means both my driver cards are good. I'm measuring the bias across the 2 meters here. And in this stage, when I'm doing this initial dim bulb test, I want to just make sure that I can adjust my bias here at the bias trimmer. Oops, wrong driver. So I can go up and down there. Up and down here, that's good. And then I want to just check my DC offset. I did do an initial check on this, and it should be pretty darn close, but it will change once we go to full power. So I'm just going to hit my meter lead around here to check the DC offset. Yeah, we're really, really good at the moment. Almost too good. Yeah, it's there. Okay, here's the other channel. So with the swapped match differential pair and the 10-turn DC offset trimmer, we can get the DC offset extremely close to 0, which is good. Last thing, we have to make sure we resolve the issue with that one channel. So there's my sine wave, and we can see that the blue trace is now nice and stable. So I think all the issues are addressed. The next step is I'm going to plug this in on full power, actually set the DC offset and bias, and then we'll ramp this up to full power and then check all of the protection circuitry to make sure it's working properly. I took some time to set the DC offset and bias on this unit while it was plugged into full mains power, and I'm set up now to do an output power test. So what I'm looking for is that both channels can produce 160 watts without an issue, and that is the case. I do have a slight channel imbalance, about a 5-watt discrepancy at full power, but that's not an issue. These traces are extremely close. And then if I continue to ramp this up, it clips right around 170 watts. So this is looking good. I did do some THD plus N measurements with the Panasonic while I had the oscillator from this device connected. And what I found is that I still might have an issue with my test rig. So I constructed this rig out of a very, very rough SX-1250 that had been through the ringer, and I think there's a discrepancy in probably the TO3 mounting clips for the output transistors. When I test the cards in this right channel, everything looks perfect. When I test them in the left channel, I get elevated distortion at high frequency. So what I did just to verify that both of these cards are good is I first tested the right channel here, and then I took the cards and flipped them left to right channel and measured the left channel card in this position, and everything came out nice. So I'll show you the results that I gathered from that in a still. Now that I've verified that all four cards are fundamentally working, I want to go a little bit deeper into the protection circuit. So remember, there's three parameters that I'd like to test. So we'll start out with the power on delay. So I'm going to switch the unit on. And there's the relay after the short time delay. When I kill the power, it should immediately open the relay, which it does. And then let's try this again. The time delay should reset. And good. So time delay is working properly. Next up, I'm going to test the DC offset detection on each channel. So right now, I only have a test signal going into the right channel, so I'm supplying a sine wave, but I'm putting 2 volts of DC offset on the input signal. So when I toggle this on, it should trip the relay, which it does. Release the signal, it comes back, trip it again. Okay, so that works. Let me reset and we'll do the left channel. Okay, same test with left channel. Okay, that's looking good. So to test the overcurrent detect, the method that I've come up with is I take a 1 ohm load that I made, I connect it across one of the output terminals, and then I feed in a test signal and slowly ramp it up. And it seems like when I put about 4.5 volts RMS across this load, it'll trip the overcurrent detect. So I'll set up for that now. Okay, I've got that 1 ohm dummy load attached to the right channel, and I'm going to simulate an overcurrent condition. So feeding in a test signal, and as soon as I ramp this up a little bit more, it's right on the edge. This should click out the relay. There it goes. So that is the protection circuit doing its job when it senses an overcurrent condition. And this is kind of a state that you don't want to be in. Some modern speakers will have a impedance curve that changes quite significantly with frequency. So there's some speakers where at low frequency, if there's like a heavy drum or a bass hit, it might dip to 2 or even 1 ohm. And if the SX-1250 is turned up trying to drive that load, you're going to get this issue. And that's kind of a bad condition to put the amp in, because you have the volume high and then the relay comes out, and when it comes back in, you're going to get an arc when the relay slaps closed because it's trying to pass heavy current. So that's a situation you don't want to get the SX-1250 into. So if you experience that condition where the relay is kicking in and out like that when there's bass hits, try a different set of speakers and see if it resolves it. And you might just have a mismatch where the amp does not play well with that speaker. All right, let's redo this test on the left channel. Okay, I've got the dummy load switched over to the left channel. Let's repeat the test. Okay, so overcurrent detect is working on both channels, DC offset protection is working, and the time delay is working. So the protection circuit is all set. And the only other verification test that I need to do is a listening test. So I'll hook this unit up to a set of speakers and listen for a couple hours to see if there's any distortion or weird anomalies or dropouts. And if everything's good, I'll be able to remove the cards and get them ready to go back to the customer. I just finished all the listening testing on this card set. So what it is, I took the test rig over to my listening area, plugged in some speakers, set up some music, and just let it run for, I don't know, maybe 8 to 10 hours while I was working on some other projects at the bench. And then near the end, I just came back and did some critical listening with a couple test tracks and just made sure that everything was doing what it was supposed to do. So all the testing went well there. Now, the final thing that I'm going to cover in this video is how to load all of the cards back into the chassis and do the final adjustment. So basically simulating what would happen if you sent in a set of cards and then you received them back in the mail. So we're starting with the empty chassis and we'll load in the cards first. So first things first, the bottom and the top cover both need to be off to reload the cards. We're going to start by checking to make sure that the main filter capacitors are drained off. So with your multimeter, connect to the anywhere ground. I usually use that jumper bar that goes between the caps for ground. and then just check to make sure you don't have excessive voltage. There's going to be something here just from dielectric absorption, but you should aim for, under 1 volt if you can. I use a little meter set up with a resistor to drain capacitors, but you can just look up, there's a bunch of videos out there on how to safely drain main filter capacitors and different little tools that you can build. But right now I'm just going to drain these down one more time before I start. So the ground is the same for everything, and I'm just going to the outside lead on each capacitor to make sure that there's no voltage across the cap. And that should be fine. So now all of the capacitors are drained, and we're safe to get our hands inside of this chassis when we need to put the pin connectors in. All right, let's get it tipped down and load in the cards. I like to start out by loading the cards that go on either side of the filter capacitors. So let's start out with the protection one. So I'm going to take the protection board and just drop it into position. And then same thing with the power supply. It goes on this side. So when we load these boards in, there's 2 holes here, and there's a little nub on the edge of the bracket here. So one of the holes gets lined up to where the screw is going to come through, and then the other hole takes that little nub. So when we lower it in here, we just kind of get it down there and make sure it's seated where that nub goes in. So once the protection and the power supply are sitting in the chassis, we can move on to the driver boards. So there's one for each channel. It doesn't matter really which one goes where, but my customer has marked with a pencil R and L on the corners here, so I'll just go with that. I'm going to put a piece of tape on the back like this just to keep this sensing diode safe. So we can undo this tape and just tip up the diode a little bit. And then these 2 are coming from the heat sink, the ones with all the colors. Yeah, just like that. And then this wire here is going to come in and go just like this. And again, you can't accidentally put it in backwards because it's keyed. So there's only one way it can go in. And then again, just double check that on the right side, you have the one with the red, blue, and yellow is towards you. That one goes in here. The other one goes in the back. And then we're going to take the diode, slide it underneath that screw. And then with your screwdriver, we're just going to twist it until it's snug. Again, we don't want to crack that. All right, let's repeat that for the other side. So I'm removing my protective tape, flipping up the diode, moving this one out of the way. I'm going to go straight down. Okay, that's set into place. On this one, it's the opposite. So this one, the brown, white, purple, orange is towards you. Okay, let's get the diode in. Good. All right, so that's it for the top. Now that the cards are kind of sitting in there, let's go ahead and put in the 8 screws and get them secured to the chassis. Okay, so to get these screwed in, I like to use a magnetized screwdriver. So I'm just making sure that this is fully magnetized. And then it's just going to make this a lot easier. You either need a very long screwdriver, one with a long shaft, or something that's a thin body, a precision screwdriver like this. Now sometimes it helps when you're trying to get the screw to set in if you go backwards until the threads kind of sit into place and then go in the forwards direction, and then it should go in nicely. And we just take it all the way down until it's snug, and we do that on the front and back of each card. Once all the screws are in, we're going to lift this up again and turn it on its side. You can also put it on the back if that's easier for whatever space you're working with. You just have to watch out to make sure the antenna is folded in properly. Okay, let's start down at the bottom. So for the driver boards, there's 2 connections down here that need to get put back into place. Then for protection, we have 4. And these ones you can get backwards, so make sure it looks like this. So the thin wires are towards the front of the chassis. That's the other large connector, and then we have the purple wires and then the multicolored wires. Okay, let's go up to the top set. Okay, this is the right channel. So this is going to be the power supply connectors here. This one, the reds are second to last. So just like that. Then here we have the green wire here. And multicolored one into this area here. Before we do the first power on test, I like to connect to measure the bias on one channel just to give me a reference when I power it on. So the bias test points on these cards are on the outsides here. So there's a little peg that sticks out near this connector and near this connector. Now there's another one for testing DC offset, which I normally don't use, which is nestled kind of underneath this connector here, so just ignore that one. So the 2 outermost ones are going to be the bias measurement points. Now that the card set is fully loaded and connected and we're set up to measure bias across one channel, I'm just going to double check the meter settings and then do the first power on. So for the connections here, most meters will have a common and then a connector for volts and ohms. That's where we want to be. And you can either measure in volts or millivolts. The reading that we're going to be getting is going to be somewhere between 0 and 100 millivolts. So if you don't have auto ranging, that's kind of the range that you would be in the low millivolts range. So I'm going to start this at millivolts, and since the unit's been off, it's sitting at 0. And for this stage, I'd highly encourage you to use a dim bulb tester if you have one, because it gives you just a little extra safety margin in case you put a connector in backwards or had it off by 1 pin, something like that. So I'm going to go ahead and power up on dim bulb. And the bias starts out low, and then it will climb as the unit warms up. So I will have these turned way down when I ship them out. So I'll just have a little bit of bias on them so that you can see a meter reading and know you've got yourself connected properly. But we're going to end up adjusting bias with the trimmer that's right here on the top, the most visible one on each driver board. So for starting out on dim bulb, somewhere around 10 millivolts is fine. We're going to go ahead and change the connectors over to the other channel. And with this, it should be done while the unit is on, so that everything is thermally tracking properly. So one hand behind the back, and then you can remove the clips from one and move them over one at a time to the other channel. And be careful not to touch any metal parts with this. It's possible that something can get shorted out. So this board I have turned all the way off. I'm going to slowly ramp it up, and we'll stop around 10 millivolts. And you see how this one's minus? It doesn't matter if you're getting a minus or a plus reading. It's going to change depending on where you have the red and the black leads connected. We're just looking for the voltage drop across this circuit. So the plus or minus, it doesn't mean anything here. Okay, so it looks like we have bias on both channels. Next, and it looks like everything came out of protection and it's safe, so we're going to power down. And next up, we're going to connect to full power, and then we'll do the adjustments for the plus minus 65 volts and come back and do the bias and DC offset. Getting to the test points for the plus minus 65 adjustment is a little bit more challenging. One of them is down here. I'll see if I can point to it. I'll move this resistor out of the way a little bit. I think the safest way to do this with a single meter is to use little alligator clips. So if we look at the connection down here, we can just bring in the alligator clip and clip onto that. So I'm probably not going to be able to catch this on camera because it's kind of tight in here. And this is with the unit off and the power supply drained. So I've got my alligator clip onto there, and the other end will be plugging into the positive terminal on the meter in a little bit. And then just use a different colored one and come in and connect to this other one. All right, let's get set up with the meter. So this time we're going to be around 65 volts DC, so we want to be in the volts scale. If you don't have an auto ranging meter, you'll probably be in the 100 volt range. And then we can start out, this one you can leave bare. The negative one You can use another clip lead or screw on a connector like this if you have this type of probe, and you can connect anywhere on the chassis. I think with the tuner installed, I just clip on a metal part on somewhere on the tuner chassis. But for me right now, I'm just going to clip it right here onto the metal. And then let's start out with the green one. So I'm just going to take my green lead here, and this you can set off to the side somewhere. Just make sure that this doesn't touch anything. So right now I'm just kind of setting it off to the side and making sure that it's kind of dangling in free air and it's not going to touch anything. And then we can go ahead and power on the unit again. So this time I'm on full power, and I'm looking for plus minus 65 volts. And this again is going to take a while to warm up and stabilize. So usually what I do is I go through all of the adjustments and then I come back and do them all again once everything is temperature stabilized. The green one that we put on back here is going to correspond to this trimmer pot here. And for all of this, I like to use an insulated tool. These are ceramic screwdrivers. They're very nice for this type of operation because you're not going to accidentally slip and short something out. If you slip inside, there's nothing conductive on this, so it's not going to damage anything. So on this one, I'm just going to slowly turn it until I get to 65 volts. And that's close enough. And then we can take our green connector and set it off to the side somewhere safe. That's got 65 volts on it, so we don't want it to touch the chassis or anything. Then we're going to grab our other lead that's tied into the other one, and we're going to adjust this side for negative 65. So this is the adjustment pot that's closer to me. And I'm rotating it clockwise to go up and counterclockwise to go down. So there's our negative 65. And it doesn't have to be super exact. If you can get it to where the first digit is 0, that's awesome. Let's go back to the green one and see if this is drifted yet. Drifted a little bit. So bring that back down. And you can kind of just go back and forth a couple times between these measurements until you get your plus minus 65 pretty close. Now again, this is going to drift with temperature a little bit, so this is fine for this stage. Okay, next up is DC offset. I usually do DC offset first only because I sometimes have a load connected, and with a load on, if there's any DC offset, it's going to skew the bias result. So I always try to do DC offset first, get it almost as close as I can to 0, and then I do the bias second. All right, next up is DC offset. This one's a little bit more straightforward. So we're going to connect at speaker A, the black lead to the black and the red lead to the red. This side corresponds to this channel and the other side corresponds to the other channel. So when we do the adjustment with where we are here, it's going to be on this driver board. So in order for this to work, we have to have the speaker A button depressed on the front of the SX-1250. And the manual is going to tell you that you need to unplug this jumper and put in a RCA shorting plug with a resistor. And I've done this before and it makes no difference. It's really not needed. I think this is what they have you make, is like a 5.6K load to plug into here. That's not necessary. You can just leave your pre-out main and jumpers in and turn the preamp down to 0 and it's going to be just fine. So now that we're set up, I'm going to power on, but we won't get a reading until after the relay clicks because we're measuring at the speaker terminals. Okay, so there's our DC offset right there. I'm just going to wait for it to stabilize a little bit before doing the adjustment. And this one is a multi-turn trimmer, which means we need a sharp flathead to get into there. And again, you want to use an insulated driver. Do not attempt the DC offset adjustment with a metal screwdriver. It's very deep in there and you're very liable to hit something metal in there and short something out. So right now it looks like we have about 4 millivolts of DC offset. I'm going to take the camera down and look at the DC offset adjustment point, and then we'll look at the meters together. So the DC offset trimmer is that blue device that's buried all the way down inside of there. So you can see it's a little bit more challenging to get to. So I'm going to get my adjustment driver in there and then we'll look at the meter screen. Okay, I've got my driver down inside of that potentiometer and I'm just going to adjust it here. And it's going to overshoot a little bit. So in this case, I'm trying to go down to negative and have it come back up to 0. So I'm just going to overshoot a little bit and let it stabilize. This is a multi-turn trimmer, so it's extremely sensitive. But with the new differential input pairs that I put in and this multi-turn trimmer, it's going to be very stable and close to 0 once we're done adjusting. So I'm just going to keep going until that's about as good as it's going to get. So I remove the tool and we're at 0.3 millivolts, so that's completely fine. I'm going to repeat this on the other side, and then we'll move on to the final bias setting. Okay, this is the left channel adjustment this time. And in this one I'm negative, so I have to spin the other direction to get it to come back up. So I'm just overshooting in the positive direction and letting it stabilize and just turning little by little until we get it to go above 0. One more little. And that's good enough for me. Okay, so you can see I've got my plus minus 65 still dangling here. I'm going to plug into the right channel's bias test points again and power the unit on. And now this time we want to wait a while, maybe 10 minutes or so, for everything to stabilize and come to temperature before we make an adjustment change. So I'm going to just let this thing stay on for a while, and I'll come back after it's warmed up, and then we'll make the final bias adjustment. Okay, this has been sitting powered on for about 10 minutes, and you can see that this has kind of stopped moving. It's stable at 36. So I'm going to go back into the upper adjustment point here and just rotate this clockwise until I get to, I'm going to go to like 60, 65. My target here is 75 millivolts. This can realistically be set anywhere from about 23 millivolts to 75 millivolts. I wouldn't go over 75. The service manual says 100, but that's way too hot. If you want some information on that, I have a separate video about the different bias levels for the SX-1250. So you see I set that to 65, and after the change it's still climbing. So now we're going to wait another 3 or 4 minutes and come back and see if it ramps up anymore, and then we'll just slowly creep up to the 75 millivolt level. So right now we're viewing it in volts, so 0.067 is 67 millivolts. You can also look in the millivolt scale like that if you prefer. Okay, a few minutes have passed. We're at 69 now, so I'm just going to ramp it up just a little bit more. And I'll come back and check this one in a second after we do the other channel. So I'm going to switch over to the left channel now. So again, hand behind the back while this is on. And the other hand can move the meter leads. Okay. Rotating clockwise. So same thing, we're going to stop somewhere around here, let it stabilize and come up. And then we'll come back in a little bit, get it up to around 75, and then check that both channels are the same. Then we're going to double check the plus minus 65 on the regulated power supply and kind of just tweak everything out until everything's stable while the unit is on. Okay, let's move this up. Oops, went a little too high. Go right around there. Let's go back and check the right channel again. See, we've come down a little bit, so just tweak that up. And you can kind of just go back and forth until you get them both to be kind of the same level. And at the 75 millivolt level, the heat sinks are going to get slightly warm. See, now we're getting really close. So the heat sinks will just be slightly warm at idle, warm to the touch. If these are getting hot, you either measured it wrong or the bias has crept up and it's set too high. Okay, let's move over to check the plus minus 65 again. And remember, on this one, we're referencing the ground to the ground connection on the meter to the chassis, or the black connection, I should say. And then on this one, I'm going to unscrew this, and we'll go to the green. So you see that's crept up a little bit, and again, just make sure that this gets set somewhere where it's not going to touch anything. So the green one was our back control, so I'm going to back this down to 65, and this will just very slightly affect the bias. So it's kind of just a little dance of going back and forth on these measurements until you get everything kind of sitting in that sweet spot. All right, back to the green one. Okay, that's looking good. And I'm going to put this connector back on, and we'll just see what the bias is like on the right channel. Okay, here and here. So once we adjusted that plus minus 65, the bias dropped a little bit, and it'll probably have dropped in the other channel as well. And the reason I'm not going up to 75 is I know it's going to drift, so it doesn't make sense to get that all the way up to 75 until we're really getting close and it's warmed up for a while. So I usually do this with 2 or 3 meters simultaneously so that I can look at a bunch of different parameters at once. But like I said, I understand not everybody has more than 1 meter, so that's why I'm demonstrating it this way. So now we're kind of getting in there. Our plus minus 65 is good. Our bias is equal on both channels. And then you just let this run and make sure that the heat sinks are just getting a little bit warm to the touch after 30-40 minutes or so. And if the temperature is equal in both, all the measurements look good, you can go ahead and start playing music through it. So that is it for the adjustments, and we're almost done here. Okay, that about does it. Thank you so much for coming by the channel and checking out this video on SX-1250 boards. If you are interested in having me restore your board set, the best way to get in touch with me is through my Facebook business profile. You can just go to Facebook, search Novolux Stereophonic, find my business page, and click on the messenger, and you can send me a DM. At that point, we can talk about pricing and if this is a good fit for you. Now, remember, this service is not for everybody. If you felt kind of intimidated by the adjustment procedure for DC offset bias and the plus minus 65 regulated supply, you're probably going to be better off finding a local technician to work on your unit. But on the other side, if you have experience replacing components, cleaning controls, and you know your way around a digital multimeter, this might be a good fit. The advantage that I offer with this service is being able to rebuild and verify the entire set, so there's no mystery. Sometimes working on these, you can get halfway through it and then get stuck where something's happening in the power supply, you're missing a voltage and you just can't figure it out. So if you just want it to be all done with quality components and everything tested and ready, so all you have to do is load in the cards, this might be a great fit. So thanks again for coming by, and we will see you on the next one.